Hey everyone, happy Friday. You've made it through, well, almost made it through the first week of distance learning. I hope everything's gone okay for you. I know it's not been ideal, but hey, we're doing the best we can. So let's get into it. Today we're going to talk about the third way of which we can find the enthalpy change for a reaction. And in order to do that, we're going to be using something known as the heat of formation, okay? And so heats of formation are going to be very useful to us. Again, this is a theoretical way that we can do it. A lot of the work's been done for us in terms of gathering that data, and we can just use that data then to do some calculations. So exactly what is the heat of formation? Well, as you can see here, it's the enthalpy change that occurs when 1 mole of a substance, and that's important, when 1 mole of a substance in its standard state, we're going to talk about what that means, is produced from its elements. So now, from its elements. So a great example of a formation reaction is the formation reaction for CO2. So we see that we have our elements as our reactants, carbon plus oxygen gas. All right, and so those are my elements. And then we're going to produce 1 mole of my product. And so the heat of formation is basically the enthalpy change that occurs for that reaction. So we call it delta H, and that F tells me that's a formation reaction. And so this is the reaction. So no matter what my product is, it's always going to be a combination or a synthesis reaction. So we're only going to have one product. We're only going to have 1 mole of that product. And our reactants are always going to be our elements. So if we should look at water, for instance, right? So if we have H2O, and I want to look at the formation reaction for H2O, we know normally H2O we're going to have, okay, we'll have H2 plus O2. Those are my two elements, and we're going to go to H2O. Now, normally to balance this, we're going to say, oh, we need a 2 here and a 2 here. Well, that's not the formation reaction because now we have 2 moles. And so to do this, instead of putting that 2 and 2, we're going to balance it by sticking a 1/2 here. So we're going to have basically this reaction in which we have H2 plus 1/2 O2 is going to give us our H2O because we want to have a 1 right there. And so that 1/2 there just tells me that I had 1 mole of H2 can react with a 1/2 mole of O2 to produce that. And then if I look for my delta HF for that particular process, we're going to see that it's negative 242. So negative 242 kilojoules per mole. All right, and so that's what a formation reaction is. And again, we'll get into what the standard state is in a second. Now, like I said before, the great thing about using heats of formation is that a lot of this data has already been gathered for us. And so you guessed it, where we can look, we can go back into the appendix, right? And so this table is big. It actually takes up several pages. It goes from A19 to A22 in the back of the book in that appendix. And it basically, you're going to see in Appendix 4 this chart. I only copied a very small part of it, right? So we're going to see selected thermodynamic data. Most of this data is collected at 25 degrees C. But again, if we look at it, what we see is a couple of things in this chart, right? We're going to see the substance here, and then we're going to see 3 columns of numbers, right? So we'll see delta HF, we'll see delta GF, and we see delta S. And so for this part, right, we're only interested in this first column. We will get to the second columns later, but for this part, we are interested in this first column here, okay? And so a couple things that I want you to notice, right? Number one, a lot of these values are going to be negative because when we have the synthesis reaction, remember, right, the whole point of these things reacting is become more stable. And so in order to become more stable, they're going to when they become more stable, they lose energy, and so they're exothermic processes. So a lot of these formation reactions will be exothermic. The other thing I want you to notice is that elements, and elements that are in their standard state, the heat of formation is 0. Anytime we have an element in its standard state, the heat of formation is going to be 0. That includes like our diatomics, O2, Cl2, I2, so on. Those guys in their diatomic form are in their standard state, and their heat of formation will be 0. And it's because there's no formation reaction for them, right? They can't be formed from other elements in a chemical reaction. So that's something that is huge for you guys to keep in mind and remember. Now, what does it mean to be in its standard state, right? And so what does that mean? Well, the standard state just means a couple of things. Number one, if I have a solid, it's pure, right? It's a crystalline solid, it's pure. If I have a liquid, it's a pure liquid. So we're not dealing with mixtures, we're not dealing with solutions, yada yada. If I have water, it's pure water, right? There's nothing else in it. If I have a gas, right, that gas is assumed to be at a partial pressure of 1 atm, right? So if I have oxygen gas in its standard state, then its partial pressure will be 1 atm. And then if I'm dealing with a solution, like we will be at some point in time, if they're in their standard state, we're assuming that 1 molar, right? So things that again, no big surprises. But so if things are in their standard state, these are the things that we kind of assume. So how can we possibly use this to figure out what delta H would be for a particular reaction? Right, so let's look at a reaction. So here we have the combustion of methane. Pretty simple reaction, right? So CH4 reacts with O2 to give us CO2 and H2O. We just want to know what delta H is for this particular reaction. Now, here's the thing, a couple things that I can do, right? If I know that I have CH4, I can look up in the appendix in the back of the book and find out that the delta heat of formation for that is negative 75 kilojoules per mole, right? If I have O2, lo and behold, I look it up in the back of the book, delta H of that is 0. If I have CO2, right, delta H, as we saw up top, is negative 393.5. And if I have H2O, right, I look up in the back of the book and I see that's negative 242. So all of a sudden I have these formations, heats of formations. So big whoop. How do I use them? Well, yesterday in the lesson we talked about Hess's law. So what we all of a sudden just do is we have some reactions that we can use now. So in this case here, if I'm talking about my CH4 and I'm talking about its formation reaction, I know it to be C plus 2H plus, or 2H2, sorry. Gonna go to CH4, where delta HF is negative 75. If I have O2, I'm not going to worry about it because it doesn't have a reaction. So CO2 would be C plus O2 goes to CO2, delta HF is going to be equal to negative 393.5, and H2 plus 1/2 O2 is going to go to H2O. Delta heat of formation of this is going to be equal to negative 242, right? And so now what I can do is, now I have 3 formulas, much like I have Hess's law. So what I can be like is, ooh, hey look, my CH4 is a product here, it's a reactant in the main, so I need to flip this. And so this becomes CH4 going to C plus 2H2, where delta HF now is a positive 75. And I'm like, okay, well, CO2, ooh, I don't have to do anything to the CO2. Right, because it's there, and then I have 2O2, so ooh, I gotta double that. right? So 2H2 plus O2 going to 2H2O. Now my delta H is going to be negative 484. And so now if I look, I've manipulated those reactions. And now if I kind of do what I did yesterday, I'm going to change colors again, and let's go to green. Right now I can cancel some things out. Those will go away. My H2s will go away. And I'm looking, and I think that's it. So now if I kind of go, I see that if I add these together, I'm going to get my CH4 plus my 2O2 going to CO2 plus 2H2O. And if I calculate the delta H for that, I'm going to see that it's a negative 802.5 kilojoules. Right, so that would be my delta H, or my enthalpy change for that particular reaction. All right, now here's the catch, right? Well, not really the catch. Here's the thing to make life a little bit easier. If we look, right, remember, we only have compounds in a formation reaction. Our compounds are only in our product side, right? So if I'm looking at a reaction and I'm using heat or formation reactions, if I have a reaction with my reactants and the compounds in my reactants, I'm always going to have to flip it. I'm going to have to flip it and then multiply it through by the stoichiometry 1, 2, 3, whatever it may be, if I'm looking at the CH4, right? So if there was a 2 in front of the CH4, I'd have to multiply that whole reaction by 2 in order to have it match out. If the products are there, then we're not going to flip that reaction, but we will have to, like we did with the H2O, multiply it by 2. And so really we don't have to take the steps of writing these out, because since we always know that we're going to have to flip the reactions that are involving our reactants, we keep the products the same because they're formation reactions, then what we can do is we can just find delta heat of the reaction is going to be equal to, and now we're just going to get a little bit fancy, but we're just going to say, okay, well that's going to be equal to the sum of the delta heat of formation of the products, right, minus, and we want to minus it because by minusing it, we change the sign, the delta heat of formation of the reactants. Right? So in this case here, we take reactants minus products. The thing about this, so if I was going to do this reaction here, right, what that would look like is I would say, okay, well, I know that I have my reactant and I have my CO2, and I see my CO2 here. I left the, it's like, where'd the CO2 go? And I left the C there. So here's CO2. Here's the heat of formation, so I'm going to say, oh, well, that's going to be negative 393.5 plus, because I want to add that, but now I'm going to say, okay, plus, and that's going to be 2 times my negative 242. And I say 2 times because there's a 2 there, and so I'm going to have to multiply that heat of formation by 2. And so that's how I get to that right there. Now I'm going to subtract that from, and now I look at my product, or I'm sorry, my reactant is methane. And so methane, we see the heat of formation is negative 75, and so I'm just going to plug in that negative 75. I don't have to multiply by anything because the stoichiometry is 1 in front, and that would be plus. And then my oxygen, I see I have 2, but we know the heat of formation for oxygen is 0, and so I just have time plus 2 times 0, right? And so now if I do that, I'm going to see that that also equals my negative 802.5 kilojoules. So again, an easier way to do it. So products minus reactants, we're going to add up the products, making sure we take into consideration the stoichiometry, and then we're going to subtract it from the heats of formation of the reactants. Okay, and we subtract it so we can change that sign. All right, so make sure you look at the daily task to get some practice with this. Let me know if you have any questions. I'll be available tomorrow. All right, guys, peace, love, happiness, and thanks for playing. And I hope you have a great weekend. See you later.